again for being here. Next up, we have Chris.
All right, thank you guys. I can give you a little introduction of me. My name's Chris Pacia. I've probably been around in this space for quite a while now. It feels like I think I got into Bitcoin like 2011. Early on I worked on OpenBazaar. I was lead developer for OpenBazaar. I don't know if you guys remember that project. I know Amir mentioned it last night on stage. It's a little bit of a throwback. And then I was also pretty kind of heavily involved in the scaling wars on the wrong side of that back in like 2014 through 17. And I was one of the handful of developers who kind of got Bitcoin Cash off the ground. So I want to talk about a project I've been working on for a couple years at this point called Illium. It's a new cryptocurrency. The way I'm kind of thinking of it is it's sort of like, if we had to design Bitcoin or really any cryptocurrency from the ground up using 2024 technology, what would that look like? And so kind of going to walk you through what that looks like in Illium and, why I think that this is at least interesting to say the least. So ever since, I got into Bitcoin, there were probably... we all knew there were shortcomings early on, right? And I would say at least these, that you could probably add to this list, I would say these are at least the big ones. Extensibility, if I were designing Bitcoin in 2009, I wouldn't have thought to add a scripting language at all. I think that was pretty amazing that Satoshi had the foresight to do that. But of course, unfortunately, it wasn't... as flexible as you would like it to be. There wasn't like a whole lot that you could do with it. Privacy, of course, being a big one, with all of our transactions being public. Then we have the zero conf issue with the transactions not really being secure. And then even after they receive a confirmation, you have to wait to receive a certain level of confidence before you can really accept it. And then, of course, we have the scalability problem. So, extensibility was sort of the first nut to be cracked with, Ethereum came out, not that long after. And so, that's, pretty much a solved problem. Privacy, I'd say I have a little shoulder shrug here. We had coins early on, some coins incorporating, like, mixing into the protocol. In fact, I worked, when we worked on Bitcoin Cash, we worked on some really advanced mixing protocols like Cash Shuffle and Cash Fusion and stuff like this. You have Monero, added, like, probabilistic privacy into it. And then, of course, Zcash kind of did it what I consider sort of be the right way by using ZK snarks to kind of, fully encrypt all the transactions. But Zcash and most other cryptocurrencies to follow that have had that type of privacy historically have not been able to extend that to smart contracts or any kind of scripting language or anything like this. So, the privacy is usually just for basic transfers and nothing else. And then the speed of the transactions, we've gotten better at that with a lot of proof of stake coins are somewhat fast to finalization, although depending on your use case, like if you're trying to buy something in person, it still might not be sufficient. And then you have, I'm kind of a bit of a fan of the Avalanche consensus algorithm. We'll talk about how we use that in Illium here in a little bit. But, I'd say Avalanche is probably the one cryptocurrency that has that level of like almost instant finalization to it. But there's trade-offs with that. And, so I have the shoulder shrug here because it's not fully solved in terms of like, can you achieve that level of fast finalization without having to have any of the negatives or any of the drawbacks to it? And then, scalability, we're still here. So this is kind of the landscape of at least kind of where I see cryptocurrency has been. And so, we're in 2024, Bitcoin came out in 2009, and we still don't have any cryptocurrencies at all that are able to do all of these things, okay? Which is pretty amazing, because these were the things that we kind of all identified very early on we could improve upon, and we're kind of still not there, at least not there in terms of, it all being done in a single cryptocurrency. So I want to talk a bit here about primarily the privacy and extensibility, kind of how we're going to do sort of smart contracts and scripting in a in zero knowledge in Illium, and we're going to give you a kind of a little bit of an overview. Hopefully you guys will be able to follow along. So ZK snarks, hopefully you know what this is. This is a kind of a programmatic zero knowledge proof where we're essentially going to create a function, and the prover and verifier are going to have prior agreement about what that function is. Could be anything we want it to be. And then the prover is going to prove that he knows some inputs to that function that make the function produce a certain output without revealing what those inputs are. Okay, the function in our example here would be foobar. And if the interface was just this simple, it would be really nice and easy to use ZK snarks, but unfortunately it isn't. So we have issues with ZK snarks that have really kind of prevented us, at least up until very, very recently, from kind of deploying them very widely. So when you're writing these functions, like that foobar in the previous example, you're not writing in Boolean logic like you would in a normal computer program. Instead, you're having to write in arithmetic logic, in basically trying to formulate your statements in terms of mathematical expressions, which is kind of like worse than trying to program in assembly, okay? Like much, much worse. We have an issue with loops. So normally in normal programming, you have a loop. You can break out of that loop at any time. You don't have to, the loop doesn't have to continue going, after you're done with your computation. But in ZK snarks, you can't really break out of a loop. So what you need to do is, let's say you're doing something like trying to verify a Merkle proof. You might need to, sometimes that proof might be very small if your set is very small, and then other times it might be very big if your set's very big. But in the cases where your set is very small, you can't just skip all the other iterations of the loop that you don't need. Instead, you have to calculate what is the maximum number of loops that I might need. What's the maximum size of my set, for example? Then every single time you need to do that maximum number of loops. So your computation can blow out pretty quickly. Along those same lines, if you have if-else statements, you have to execute both sides of the block, right? So if one side is a very small amount of computation and the other one's a large amount of computation, you're going to be executing both of them, and you're going to have to bear that expensive cost. So it's definitely not like normal programming, and it kind of limits what we can do with it. So in recent years, and this is like very recent stuff, like the last year or 2 years, people have been putting in a lot of effort to try to make systems where we can use ZK snarks more like regular programming. And so the one that I use here in Illium that I'm going to talk about is called Lurk. Lurk is a Turing-complete programming language. It was developed by Protocol Labs. I don't know if you guys, they're the same ones who make IPFS and Filecoin. The lead developer for Lurk, his name's Chimid Kurdzang, I believe, if I pronounced that right. And he wrote the ZK snark implementation for Filecoin, which sounds like it was a nightmare to create. And so he kind of took those lessons that he learned from writing that in Filecoin and applied it to Lurk. So the basic idea here, what we're looking to do, is we have in computer science, we have this concept of like a universal Turing machine, something that can kind of execute any sort of computation that we want. What we would kind of like to have is a universal circuit where we can create a proof for any kind of computation that we want. And so part of the solution to this has been with some advances in cryptography in recent years with the recursive snarks and the incrementally verifiable computation. The basic idea here is we're going to have a circuit that we're able to kind of sort of step through our program and go through that circuit multiple times in order to execute our program. So it then does sort of beg the question, like, what should that circuit look like? Because we do have still have these underlying issues with the performance of the ZK snarks and the optimizations. So we want our circuit to be kind of as minimalist as we can make it, for performance reasons. So what is kind of the minimalist type circuit that we can come up with for this like universal circuit concept? Then we have this real big throwback to 1960 here, recursive functions of symbolic expressions and their computation by machine by McCarthy at MIT, where he's introducing Lisp, right, the Lisp programming language. So Lisp is a very, very minimalist programming language that it creates you have a CEK machine where basically you take an input, and you have a very minimal state transition. It produces an output, and you can kind of recursively step through your program that way until you can execute the full program. And so something like this is basically what Lurk is implementing inside the circuit as kind of a very minimalist form of a programming language. So I asked ChatGPT to give me a diagram for a CEK machine, and this is what it came up with, which is not even remotely close. But I mean, you can think of it as we're going to have a program. We're going to break our program up into multiple steps. And for each step, you have the input into our circuit. We perform some computation. We get an output. That output then becomes the input to the next iteration of the circuit. So when we create a program, this is a little program calculating a Fibonacci sequence. We can, in this example, we've got 89 iterations through the circuit. So we're going to step through our program, iterate through our program this way, and at the end result, we're going to get a single succinct ZK snark proof that proves the correct output, that the inputs that we have to this program produce a particular output. The nice thing about this is we're back to using Boolean logic again. We're not using arithmetic logic. Loops work the way you think they would. If you can break out of a loop, you don't have to calculate what is the maximum number of loops that I need to make. If statements work like you think they would, if you have expensive computation, you can just skip that. In the else block, or whatever, you only execute one side of that block rather than all of them. So basically, we're back to normal computation again. So how do we use Lurk and Illium? All transactions have a ZK snark proof attached to it. The proof, this is UTXO model, by the way. We prove that the inputs that we're spending in our transaction exist in the set of all outputs in the chain. We prove that the inputs have not been previously spent. We prove that the output amounts do not exceed the input amounts. And we prove that the spender is authorized to spend the coins. And we do all of this in zero knowledge. So basically what this is we've just recreated Zcash, essentially, right? This is very similar to how Zcash works, albeit we're using a little different cryptography under the hood, but same concept. But can we go a little further? So in Lurk, we have there's this kind of built-in concept called functional commitments, where any expression, you can basically get a hash of it for all intents and purposes. So here we've got a function, f of x. We can call that commit function to get the hash of it. And then later on, we can open it up and execute that function just by calling this open command. And in this case, we have an output of 122, and we could prove that we know some input, which is the number 5 in this case, that makes the output, that produces that particular output without revealing our input. So with this concept of functional commitments, if you think about it, I don't know if your brain goes the same place that mine does, but it reminds me quite a bit of the pay-to-script hash in Bitcoin. So in Bitcoin, some address types have their pay-to-script hash address, where you create a script in Bitcoin and you take the hash of it. This hash becomes your payment address, essentially. So your payment address that you send coins to is just a serialization of this hash. And then when you want to spend the coins in Bitcoin, the spender has to provide this script as part of the transaction. And the full nodes on the network will verify that the script the hash of that script matches the hash that you committed to in your address. If it doesn't, it's an invalid transaction. So basically, we do the exact same thing in Illium, where all addresses are pay to script hash addresses, where the script hash in this case is a lurk functional commitment, where the user is committing to any kind of custom locking script, if you will. Unlike Bitcoin, however, this is a Turing-complete language, and you can do any kind of computation with it that you want. And just like with Bitcoin, when you go to spend your transaction, the spender has to provide the script, and then we verify that the hash of the script matches the hash that was committed to in the address. But all of this is done in zero knowledge, so we're unlike Bitcoin, we're not revealing this script to the network. Okay, so all of this kind of remains hidden. This example here is particularly interesting. This is a multi-sig script on Illium. Privacy coins have typically had an issue with multi-sig. They can do basic transfers pretty easy, but then you start trying to say, well, how do I do multi-sig? And it starts to become a mess. Like some of them have to do like a Schnorr aggregate signature where you have many rounds of communication and the user experience really just breaks down. But with this, because we can create any script that we want, we're kind of back to multi-sig, kind of the way we're all familiar with it, which is pretty great. But can we do more? So when the script executes, we have these two parameters, private and public. We pass into the script as it's executing these arguments here that allow the script to inspect all the private and public data that's part of the transaction, and then make decisions whether to lock or remain locked based on what this data is. And the private data and public data, it contains all the data, not just about the current input being spent, but all the other inputs and outputs on the transaction. So you have basically full covenants that you can do things like this script is pretty much saying like these coins can't be spent unless they're being sent to this particular address. Okay, so we're just putting a restriction on where the coins can be spent. We can one-up that and take it just a little bit further, and we can make what I would call a recursive script. And now this isn't a recursive function because we can put a recursive function just inside here and just iterate over that as much as we want. A recursive script in this context is every time what this is doing is it's saying in order to spend from this script, it has to go back into the exact same script. Okay, can't go to any other script. So you can think of this as sort of every spend of this UTXO is an iteration of a loop essentially. And in every iteration, I can decide which one of these methods I want to call. So this is starting to look very much like a smart contract where we have methods, it's deployed on the network, and we have methods that we can call. And from there, we can just add state to it. So outputs can have state attached to it. They can read the state, they can mutate it, they can manipulate it. You can, in this little example, I have a method called increment counter, which just reads the state and increments an integer. So basically, we have all the components of a smart contract. We have a script that's deployed on the network that has methods associated with it, that has state associated with it, that you can make repeated calls to it. You can manipulate that state. Contracts can interact with other contracts. They can make function calls on other contracts. Other contracts can call their functions or read their state. So we've got everything. And all the components of a smart contract, but all in zero knowledge and all without revealing any of this information to the network. So when we look at a transaction over the wire, this is really all you see. And there's really no identifying information here. So you don't know, is this a basic transfer? Is this a smart contract? Was this a token, right? We could be sending tokens around the network instead of, Illium coins. We don't know because it all just looks like an encrypted blob to anyone looking at this. Another nice thing we see, there's a fee attached to this. This fee is just similar to Bitcoin. It's just there to prevent spam. It's not a gas fee, so we don't have a need for gas because all these transactions are going to verify in constant time. So it doesn't matter if this is a basic transfer or whether it's the world's most complex smart contract, that they all take the same amount of time to verify. And because they're taking the same amount of time to verify, we don't have to do what like Ethereum does and start charging fees per opcode and things like this, where the more complex your smart contract is, the bigger the fees you have to pay. Okay, it's all constant. Okay, so there's more to Illium than this, but that's just kind of an overview of how we sort of achieve this zero knowledge property and build a completely private blockchain. So what do we have? Extensibility, yes. Pretty much anything that you could do on a traditional smart contracting platform, you could do in this model. Privacy, right? All transactions look the same. You can't tell one from another. There's no private data being leaked on any of these transactions. Fast, I did mention, briefly mentioned Avalanche. Doesn't have any relation to the Avalanche network, the AVAX, who's the sponsor of this event, except that I do use a custom version of the consensus algorithm that I wrote with some tweaks to it to address some of the kind of perceived, you know, maybe some security trade-offs that they make. So I could elaborate more on that later if you ask me about it. And then scalability, haven't really done anything new with scalability, but a lot of the cryptographic primitives that are in place could potentially be used as a foundation for things like proofs of consensus and succinct blockchain, because all the tools to do that are still there. So we have an alpha network live right now. If you wanted to test it out, there's a faucet where you can get some coins. Hoping to move to a more formal test net middle of this year or so. And depending on how all of that goes, maybe you know, mainnet launch later this year, early next year. Okay, thank you.
Awesome. Thank you so much, Chris. And now if we can have the lights up so we can see everyone's beautiful faces. Lovely. Do we have any questions? Closer.
What cryptographic backend do you use for zero knowledge?
Nova?
Nova?
Yeah.
Oh, very cool.
Yeah.
We should talk.
Yeah, it's not, I should say Lurk is using Nova, and so I'm using Lurk, so by extension it's Nova. Other than kind of, you know, following the development and the pull requests and everything, it's I'm not like super deep in my knowledge of how it works, but yeah, but I can talk about it, yeah.
Yeah, what's the catch? No solidity compiler probably.
Yeah, yeah. I mean, someone could probably make a compiler that could compile Solidity into this. You know, it's just the model's a little bit different. So that, I mean, I don't know if it would be like, it's not going to be like a one-to-one port of a contract directly over to this, but yeah.
Awesome. Do we have any other questions? No? Awesome. Well, thank you again so much.